Hi again. Let's talk about amino acids a little bit more. Okay, it's Labor Day. I'm here in the department, in my office, but nowhere better to go. Hope you guys are getting some rest and having some fun. All right. So the structures of amino acids. We talked about different amino acids. This is the basic structure: amine, acid, and there's a CH that's called a methine. When you have one hydrogen attached to a carbon, that's methine, methine. When there are two hydrogens attached to a carbon, that's called methylene. When there are three, that's methyl. Methyl, methylene, methine. So this is a methine. The only amino acid that's methylene is glycine because R equal to H. The weird amino acids that stand out, this guy is sort of weird in some way. This is definitely an amino acid that stands out. I almost forgot last time when I was talking about it. Um, Other amino acids that are weird, in my mind, isoleucine and threonine, they both have two chirals. Each amino acid has two chirals. This is always S if it is natural. S, S. And if you write the nitrogen on the left, carbon on the right, and if you write the CH, the methyne carbon up, not down. If it is up, then the group is always sticking out, drawn with a wedge. Okay, that's sticking out toward you, not this way. That's how you draw the amino acid starting with nitrogen on the left and the carbon on the right, and the CH is up. Because if the CH is drawn down like a little well, like a little V, then the R group has to be drawn with a dashed line. We'll talk about it a little bit more today. Yeah. Um, Glycine, alanine, valine, isoleucine. It's got like a butyl group, sort of like a sec-butyl arrangement. This is leucine. That looks more like an isobutyl group. This is how the isobutyl group is. Iso means isobutyl, isopropyl groups have a V, like a little split at the end of the side chain. Serine has an OH. It's kind of like alanine. Attached to that is an OH. Threonine is basically serine with an extra methyl group. Okay, so serine and threonine, they're very similar. Another one with the hydroxy group is phenylalanine. This is phenylalanine, CH2 with a benzene ring, that's called phenyl. And phenylalanine is phenyl with, tyrosine is phenylalanine with an extra OH. Okay, so OH guys are three of them: tyrosine, threonine, and serine. One only with SH is cysteine, cysteine. Okay. What else? Another one with a sulfur, but then it's not SH, it's methyl. Okay, thiomethyl group. It's called methionine. Two with carboxylic acid side chains, this guy and this guy. The one with a one CH2, that's aspartic acid. This is glutamic acid. Similarly, asparagine and glutamine. It's the side chain itself is an amide. Primary amide because it's carbonyl with NH2. Carbonyl with NH2. Some other crazy ones. Arginine. It takes a little while to draw the molecule, the side chain. Three CH2s, three methylenes in between the methine from the backbone of the amino acid. 1, 2, 3. then NH, then carbon, then two more nitrogens. Okay, it's kind of like a starry nitrogen arrangement. Okay, this is a nitrogen, that's a carbon, that's a nitrogen, that's a nitrogen, and this nitrogen is attached to a three-chain CH2, 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 CH2. Lysine is plain and simple primary amine at the end. There are four methylenes in between. 1, 2, 3, 4. Tryptophan has a bicyclic aromatic ring on the side chain connected with one CH2, connected here next to the junction, and the nitrogen is at the other end of the 5-member ring. Yeah, you have to just kind of memorize it. Histidine is pretty critical. This guy is pretty important. Histidine has one CH2, kind of like this, but it's a imidazole ring on the side. Imidazole is also an aromatic ring. This itself is an aromatic ring. This is an aromatic bicyclic ring. This is aromatic. This is aromatic. So how many aromatics we have? 1, 2, 3, 4. Yeah, I think that's it. And then proline. Proline has the cyclic structure. The nitrogen is sitting in the ring, okay, like a cyclopentyl ring. This would have been called pyrrolidine. Pyrrolidine, Pyrrolidine, pyrrolidine. Pyrrole or pyrrole would be the aromatic version. No carboxylic acid, CH, a double bond here and a double bond here. That would have been an aromatic ring. Okay. So this is what the village of amino acids look like. Okay. All right. I'm going to erase and let's talk about how you make the amide bond and how you get into the peptide world or protein world, connecting amino acids one after another. We did have some fun till yesterday. We drove up to the Bay Area on Friday. Saturday, we drove to a place called Fort Ross. That's a little south of Mendocino, northwest corner of California, north of San Francisco. There used to be a Russian territory. When the Spanish people came, the Russians came and they were living there. There was a little fort. Pretty cool place. Really cool. I strongly recommend if you are looking for a two-day break, I would go there if you like history and looking at how US used to be some 100 years ago. It's really nice place. Okay, my Labor Day laboring is done. This is it. What I would like to do right now is amino acids, before I get into the amino acid business, because there is something tricky, okay? So let me show you how an amide bond is made. Carbonyl chemistry, we already talked a little bit about carbonyl chemistry, okay? So we are talking about amino acids. Don't know if we should put our date today. Okay, this is my friend from Richmond, Virginia. It's a long story. 9-2. Okay. 9/2/2024. And so this is, let's say this is number 2, version number 2. And we're going to start talking about amide bonds. Okay. So that's going to be kind of like our guideline. Since it's a holiday, I'm allowed to text. So I'm just going to text him that I'm making a video preparing I'm going to also turn off my you don't want that thing again. Okay. So we're going to talk about amide bond. Okay. So there has to be a carbonyl compound and there has to be an amine to make that molecule happen. So if you remember very quickly, I'm going to draw them here. So the most reactive is acid halide. Then the next guy, if you remember, is anhydride. Then the next one is carboxylic acid. Then the next one is an ester. I'm just using the same color, okay? And the next one was an amide. And let me draw a secondary amide. So this is an acid halide, anhydride, carboxylic acid, ester, amide. So this is your target. This is where you want to go, okay? This is your target. And the whole idea is, how do you make that molecule from the starting compounds? And the most available starting compound is this. This is usually the starting point. Okay? So the idea could be that since we are rolling downhill, why can't we start with the carboxylic acid and use an amine? What about this amine? We add a nitrogen. Can this reaction work? Let's check it out. Okay. So this is kind of like our guide again. This is on the side. Okay. So let's check it out. Okay. Let's start with the carboxylic acid. Let's say we start with this particular carboxylic acid. The way you would name this carboxylic acid, there's a carbon here, 1 and 2. So this guy has 2 carbons, and it originally, I'm not really ready for a speech today. Looks like I'm also getting a little hungry. 2 carbon chained alkane is ethane. Okay, so we have to use ethane and make it sound like an acid. Okay, so this guy's name is let's use the word ethane in black. I am not prepared mentally. This is ethane. I mean, this is not ethane, but this is how you write ethane, right? That's ethane. So what you do is you take the E off, and carboxylic acid, we make it sound a little bit different. We make it sound like ethanoic acid. So 2 carbon chain carboxylic acid is called ethanoic acid. E gone, oic acid is added. So I used color coding. Methanoic acid. They have their trivial names. This is acetic acid. This is vinegar. Okay. When you have 1 carbon and a hydrogen, that is called methanoic acid. The trivial name is formic acid. You may have heard about that. Okay, ethanoic acid, propanoic acid, butanoic acid, blah, blah, blah. Okay, and the numbering starts from here, it goes out this way. Okay, so if you have something like a fluorine at carbon number 3, then you call it 1, 2, 3, 3 chloro, 3 fluoro, 3 bromo, 1, 2, 3, 4 butanoic acid. Okay, so you take that and you take this amine. I'm going to draw this amine in blue color now because it's an amine. Okay. This is a primary amine because it has 2 hydrogens attached to the nitrogen. And this guy's name is going to be methylamine. Okay. So what you want in a nucleophilic acyl substitution reaction, the first thing that happens is this. The nucleophile with the lone pair or the negative charge, if it is a negatively charged strong nucleophile, attacks the carbonyl carbon, pushes the pi bond between carbon and oxygen up, makes the tetrahedral intermediate temporarily with an O minus. Then if you have a leaving group, this guy has a leaving group, not great, not terrible in the middle. And then it's that negative charge. I'm just going to kind of like taking a shortcut. I don't have the patience to show you the mechanism. That's not the point today. Okay, it goes up and the negative charge kicks back, and this is what happens. And you're supposed to get your product, right? You're supposed to get this guy. It's positively charged, and at that time, you use a base, and the base could be various different things. Base could be OH minus, base could be another amine, base could be the lone pair from here, base could be the lone pair from here. So we do not specify what exactly the base is going to look like. We just say the base is going to be uppercase B with a lone pair. I'm just showing you just a little bit of mechanism because this can be confusing. I'm not sure how you learned it, how you learned mechanism in 128A and B. I usually follow certain guidelines. I'm not sure if everybody teaches the same way. So I want you to kind of know how a proton is lost or how a proton is added and how we should. So B means base. What is a base? Base is something that grabs a proton. Okay, the base grabs a proton, and this bonding electrons between the nitrogen and that hydrogen goes back, and this is an equilibrium arrow because adding a proton and losing a proton, generally speaking, is a reversible process. So what does the final product look like? The final product looks like this. All happy, and you got a lone pair. That's this lone pair. That's this bonding electron between the nitrogen and hydrogen. It's easy to lose a proton. That's why you need to have at least one hydrogen attached to that nucleophilic center for it to be a nucleophile. If it did not have any hydrogen, it can never make itself neutral by returning its lone pair. That's why tertiary amines cannot function as a nucleophile. They will always stay protonated. They have nothing, no hydrogen to kick out to become neutral again. Make sense? Hopefully it makes sense. So this is the premise. This is what you think will happen, but it doesn't happen so. For other reactions, like going down from here to here, 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 all these arrows, they all function pretty much following that mechanism. Nucleophile attacks the carbonyl carbon, pushes the double bond up, kicks back, leaving group goes up. The problem here is the nucleophile, which is methylamine, acts kind of sleazy and a kind of a not a very respectable in a very respectable manner. It goes after a low-hanging fruit. It gets lazy. It looks around the carbonyl compound and finds something easier to do. Hitting a carbonyl carbon is more hard work than grabbing a proton and like with its lone pair, right? So what it does instead of doing that, this does not happen. This does not happen. This does not happen. This does not happen. It does something very derogatory and very shameful. What does it do? Well, it plucks a proton. Not from there. My bad, my bad, my bad. I am probably not supposed to be doing this today. The lone pair plucks the proton, and this is how we actually show it. Plucks the proton, the bond between oxygen and hydrogen folds, and it pushes the other oxygen up. Okay, so this does not happen. This whole thing does not happen. Okay, instead, what happens is that happens, and that proton is gone. That proton, the acidic proton from the acid has been picked up by the amine. It already had two hydrogens, and this used to be its lone pair. That's the lone pair, but now it has a proton stuck there. Okay, so what is it? It's a cation and an anion. What kind of bond exists between a cation and an anion? Ionic bond. Okay, so this bond between here and here is an ionic bond. So what is this species? This species is a salt. Salts are like rocks. This is a darn salt. So it's dead. It cannot do anything. So if you add an acid and an amine together, hoping for an amide to happen, unfortunately, amide is not going to happen. What you will end up getting is a salt. This is how we remove excess amine. This is how we remove excess amine or excess acid by using an appropriate base or an appropriate acid. It could be one normal HCl or more dilute HCl or sodium hydroxide, different concentrations to wash. What happens is once you wash it, the excess acid or excess amine will form a salt. Once you form a salt, this is going to be water soluble. That's the terrible looking bead. Okay, it's going to be water soluble. So if you're using a separatory funnel, you can give it a wash with acid or base, depending upon if you had excess of base or amine or acid, then you can easily remove it. You don't have to run a column. You don't have to run an HPLC. You don't have to run any prep TLC or anything of that sort. You can just give it a wash as long as the rest of the molecule is not going to be falling apart with excess acid or excess base. You have to check that. You have to make sure that you're not going to be destroying your compound. You can give it a wash, and your final organics layer is going to become more and more clean by getting rid of excess of something, acid or base. Okay. I hope you understand. We can talk about it if you have further questions. If it is going over your head or your old memories are not really lining up properly, then you can ask, just ask. So this is a problem. Okay. So what we do instead, we don't go from here to here. So here to here is not possible. It doesn't work. So what we do instead, we take the acid. I'm going to show you the very traditional methodology. We can talk about the modern methodology later on. Okay, let's learn the basic stuff. Let's relearn or refresh your memories with the basic stuff. You take the acid, you convert the OH into a chlorine by running a pretty old and trusted reaction. Stinks. It's called thionyl chloride. I recommend that you read up. Let this become your homework. Okay? Check it out because at some point I'm going to be asking you a question, including the mechanism of the reaction. Okay. Thionyl chloride and heat. Delta means heat. Okay. So what happens as a result of this? You convert it into a chlorine. What's the advantage? Chlorine is an awesome living group, but it doesn't have that annoying H, acidic H. It's a great living group. It's the best living group, one of the best living groups. Now you converted this into a chlorine. Now you're safe to use after you clean up the stuff. NH2 methyl, same molecule. Okay, same molecule, methyl amide. And what do you get out? Now this time, what it does is boom, up, back, and out. And then eventually it loses a hydrogen that way. Okay, I'm just going to draw the final product. You get a beautiful amide bond. This is not how we make an amide bond. We use a little fancier methodology using something called EDCI. It kind of produces a living group, not chlorine, but when you use EDC or that series of activating agents for the carboxylic acid, it's a much milder reaction. These reagents have been developed over the past many decades, and they are awesome. Some of them are so good that there is hardly anything else to improve on them. Okay, so we'll talk about it some other time. So the heat and production of using a stinky compound like thionyl chloride, the byproduct is HCl. The HCl vapor gets into the hood, and if the hood is not working well, it kind of stinks up the lab. You feel like having breathing problems, and it gets into your nose, sticks there. It's kind of a nasty compound. It's not. It doesn't have any target organ. It's not going to cause cancer or have like CNS effect or something like that, kidney effect, whatever it is. But it's just an annoyingly caustic and pungent, has a pungent smell. It's just a terrible compound to use in the lab. At the end of the reaction, you have to rotovap off the excess thionyl chloride. That's not pleasant. If you're not careful, then it can stink up not only your lab, but in the hallway and your neighbors. Okay, so you get your amide. You get your amide. So what's the amide? This is your amide. That's your amide. This is your amide. This is your amide bond. So that's the bond that exists between two amino acids. Okay. What kind of amide? It's got one hydrogen. So this is a secondary amide. Make sense? So I'm going to take a picture of the board, maybe a little bit later. So this is how you make an amide. Okay. So this is synthesis. This is synthesis of amide bond. Okay. Let me just show you another synthesis, the fancy synthesis of amide bond. One of the early fancy synthesis of amide bond. Okay. So this is one, and this is another one, another methodology, which is much more convenient. You take the acid, okay? You take the amine, there is no stepwise reaction. You take the acid, you take the amine, and you react it with what is called EDCI. I'm not gonna write it down. EDCI. Sometimes along with EDCI, you use something called HOBT. I do not know if I should write it down, but I'm just going to write it down in parentheses. We don't use it. HOBT, and then we usually use an apolar protic solvent, something like methylene chloride. Okay. Out comes your product with some other junk that comes along, and you get your product. Okay. If you do a really good wash, if you work it up with acid and base, if you do that, it can be super clean. When we make our DEET analogs, this is how we make it. Okay. If you're curious, it's not going to be, I'm not requesting you or mandating that you guys need to figure out what EDC is, what HOBT looks like, things like that. But if you're curious, just take a look at it. Like, what does this molecule look like and how does it work? Okay. It all depends on your motivation and your drive and where you're going, and if it aligns with that. If it is not your thing, cup of tea, then don't bother. Okay. So this is how amide bonds are made. So I thought I would talk about that. Let me take a snapshot of it because you know that I have been taking snapshots of the board when I'm preparing a video because the resolution is better. Let's just take a quick picture. Okay, I'll upload it. So this is how amide bonds are made. So let's get into the world of amino acids again and see how they look like after you have made connected two amino acids together. Yeah. Let's erase pretty much everything. All right. So let's draw an amino acid and let's draw another amino acid and let's see if we can couple them. Then you will see why the concept of protecting groups have come about. There is a reason for us to use a protecting group. So let's say that we are going to connect two of the most basic amino acids. We're going to connect the carbonyl end of a glycine to the nitrogen end of an alanine. Okay, let's draw them out. Okay, so this is glycine. Okay, CH2, that's glycine. Glycine, whole name, GLY, three-letter symbol, and G for one-letter symbol. Now down here, let's draw alanine. This has got a methyl group sticking out. When you draw it like a mountain, nitrogen on the left side and carboxylic acid on the right side. Okay, and this is called alanine. ALA, one letter code, ALA. Okay. This is what you want to generate. You want to connect the C end of glycine with the N end of the alanine. So this is where you want to make the connection. Let's make it a little bit thicker so that you guys can see. I know that green is hard to see, especially in a video. Good luck. You know what? What the heck? Let's just make a line. Looks like a question mark. The green line is what you want. Okay. I wish this was like a real class, then I could just bother you with some annoying questions. I get it out of that. So you want this lone pair, you want the lone pair on alanine's amine to attack the carbonyl of the glycine. Why should it happen that way only? Because you realize that you have alanine. It's not just one alanine. If it was just one alanine, maybe you could find a way to make it go that way. But when you have a gram of alanine or 10 milligram of alanine, or like 1 microgram of alanine, there are like hundreds of millions or thousands. I don't know exactly how many. You have to do some gen chem calculations, like how many molecules, Avogadro's number, right? How many molecules are there? So this guy will be, there are more alanines sitting around. There is another alanine somewhere, right? There is another glycine somewhere. So what's the guarantee? What's the guarantee that if you put glycine, so if you take glycine and alanine, and if you cook it with, if you take glycine and if you take alanine, it'll be a lot of fun. You'll make a library of dipeptides. More than dipeptides. It's going to be a beautiful mess. If you take this guy and this guy with the carboxylic acid, and if you cook them with EDC, oh, it'll be so much fun. And let's say methylene chloride. What will you get out? Will you get out just one compound? And what, this is your desired compound. Desired dipeptide. Dipeptide means it's a peptide with an amide bond. 2 amino acids are contributing to the dipeptide. Okay, this is what you are dreaming of. You are dreaming that, oh, you know, my dipeptide is going to look like this. There's going to be a beautiful amide bond between the carboxylic acid of my glycine and the amine of my alanine. Oh, good luck. That's not going to happen. That's going to happen. It's wrong if I say it's not going to happen. It's going to happen, but many other things will happen. So now it gets a little tricky. So you always draw the amino acids when it's in a chain. When it's like a peptide or a protein, you just draw them like zigzag lines. Okay. So the next line is going to be this way. Okay. It's not going to be a mountain, it's going to be a V. When you draw the V, the methyl is up when it's written as a mountain. When it's written as a V, the methyl is drawn with a dashed line. Okay, because that's the right stereochemistry. That's still an S stereochemistry. If you're confused beyond recovery, think about stereochemistry, what you learned in 128A. If you need help, I can make a video of stereochemistry. I would expect that I don't get dragged into this rabbit hole of making videos. I only make videos when I have to, and it's going to get more and more busy for me and everybody else. So I'm requesting you to please, please, please review stereochemistry, talk to each other. If you don't talk to each other, don't bring yourself up, it's going to cost you points. I'm not trying to be mean, but there has to be some, basic requirements, expectations from you guys, because you're in a grad level medicinal chemistry course. I expect you to know certain things. I'm willing to help, but you have to help each other first. Try to help yourself. And then if all fails or doesn't, don't get appreciable results, then come and talk to me. I'll figure out something. Stereochemistry, I would like to talk to you guys in person, maybe additional classes, or sometime we can meet at some point, whatever, and then figure things out. So that you draw the methyl group as a dashed line. That doesn't mean it's our stereochemistry, still is. And then you want this carboxylic acid to be open. Okay? As I said, that it will probably happen, but what's the guarantee that this is going to attack here? Why can't it attack here? So it's going to happen. It will attack there. It's going to be a statistical distribution. Like if a dog has an itch for its tail, if a dog is trying to bite its tail, if it is just by itself, it's going to bite its own tail. If there are other dogs, I don't think it's a dog thing, but just for the sake of argument, don't argue with me that Dr. Maitra or Shantanu, dogs don't do that. Dogs only go after their own tail. In a hypothetical situation, on a different planet with mutant dogs, let's say they like any tail. They don't discriminate among their tail and somebody else's tail. There are 10 dogs in this room. They will go after their own tail and somebody else's tail, right? So the amino acids follow that same rule. Okay, so that's going to happen. It's also going to attack its own tail. That's going to happen. So this is number one possibility. This is number two possibility, right? So two things can happen. And then what's the guarantee that glycine's amine cannot attack alanine's tail, or glycine's amine cannot attack its own tail? That will happen too. So let's draw it in different color. So this guy can do that. This is number three possibility. And this guy can also do that. That's number four possibility. That can happen. Four different products can happen. More problem. This is not it. More problems. More problems are, I'm going to give you like a pause for like half a minute, even though it's a video. I'm trying to like trigger some thought process. Can more disaster happen? But the answer is yes. More terrible things are going to happen. Okay, I'll try to keep my mouth shut for like a few seconds. 30 seconds is too long. 15 seconds. 1, 2. Yeah. Let's use the product that's written on the right side of the board. North east corner. Northeast corner. My geography is kind of sketchy. My navigational skills are even sketchier. Okay, so when you have a dipeptides with an amine on this end and a carboxylic acid on that end, what's the guarantee that they won't react with each other? Yeah, you are just producing another species, a two-dog species with an amine and a carboxylic acid. It's kind of like a dipeptide with open complementary functional groups. It's ready to react with itself. It's ready to react with any of those guys, two other amino acids. So the result is going to be a disaster. So the chain will probably increase in length. You will probably make like a variety of polymeric. What's the polymer here? It's a natural polymer. It's going to be some kind of a crazy assortment of peptides, dimer, trimer, tetramer, pentamer, hexamer. It's going to be a disaster. It's going to be a complete disaster, right? It's a bad idea. So this doesn't work. Okay, this will happen. And I'm just going to write down and many more peptides will, that's not how you write, will form. Okay, it's going to be a mess. So you want to avoid that. This pen is dying. Okay, so you don't want to do that. So how do you do that? How do you solve the problem? So let's block this area. What is that called that you put on the dog's mouth when you don't want your dog to eat something or attack someone else if it is not fully trained? Muzzle, something like that. I'm just going to call it like a mask. Okay. So what you want to do is, so this is a problem. So that's a problem. So how do you solve the problem? Well, so scientists, chemists developed protecting groups. Protecting groups are like a mask that you put around your amine face or your carboxylic acid tail that doesn't look like a carboxylic acid, but that can be quickly removed when the need is over to make it look like a carboxylic acid again, or make the amine look like an amine again. Okay, so different protecting group chemistry has evolved. Some of them are acid sensitive. That means in the presence of weak acid, it can come off and become an amine again or become an acid again. They can be base sensitive. If you want them to be acid stable but base unstable, that can be done. Sometimes they can be taken off using completely different methodology, like hydrogenation, things like that. Okay, so solution to this problem. Protecting groups. Protecting groups. Protecting groups are, I'm not going to, again, delve too much into the protecting group territory. I'm just going to tell you that these are some of the protecting groups, and keep this video, terminate the video right after we do that and show you like a few compounds with the protecting groups on. So you can buy, I'll just give you a few examples. So if you want, in this case, we want this guy, right? You want the carboxylic acid of glycine to be reactive, and you want the amine of alanine to be reactive. But you don't want the head of glycine, the amine of glycine, to react. You want to protect that, okay? So you want to You want a protecting group here, PG. I know abbreviations can be overwhelming and annoying and irritating, but I don't have that much space here. You want to protect the N end of the glycine, and you want to protect the C end of alanine. Easy. C end of alanine is easier than the other one. So what you want to do is, you want to start with glycine. And use a protecting group. If you want acid sensitive, we will use a group called BOC, BOC. I'll show you what BOC stands for. We'll use a protecting group that's acid sensitive. It can be tricky because this is an acid. So this guy can itself take the BOC off. So you have to run the reaction very carefully. So you buy it from commercial resources. They're pretty cheap. The amino acids with different protecting groups, they're affordable. If you don't really have to have like $1 million grant to afford them. Okay? You take this guy, this is protected. This is the if this is the head of a dog, then the dog is wearing on one of those muzzles or whatever you call it. Okay. With my sketchy pronunciation. And you want this to be open. You don't want to mess with that. And you want to use the amine end of the alanine. But you, on the other hand, you want the carboxylic acid end of alanine to be not an acid. You want it to be temporarily blocked. One of the easiest things you can do is buy it as an ester. And you don't want to use a reaction condition where the amine can react with the ester. Okay, you want to use a mild reaction condition. So thionyl chloride reaction condition to convert it into a Cl, bad idea. BOC is going to come off because when you try to convert this guy into a chlorine using thionyl chloride under heat, it'll produce HCl in situ in the reaction. That's going to take the BOC off. It's going to be another mess. Okay, so EDC coupling. So you take these two, okay, this plus this, and you react it with EDC, EDCI, and let's say methylene chloride. Everything goes well. When you work up the reaction at the end of the reaction, when you are working up, like cleaning up, throw it in a SEP funnel and give it wash. No washing with acid. You can give it base wash, but you cannot give base acid wash. So in principle, since you cannot give an acid wash to get rid of this excess amine, you want the excess amine to be your limiting reagent, right? That's how you set up your reactions. Maybe you can use one equivalent of this and slight excess of that. One equivalent and 1.1 equivalent of that, 1.2 equivalents of EDC, HOBT, yes or no, and then methylene chloride. You run the reaction at room temperature and get the product, follow them by TLC or whatever. They don't have any chromophores, so it's going to be challenging to see them under TLC. You can use different stains. This is organic chemistry before you make your great molecules for screening in biological assays, right? So what you get out of this reaction, the NH BOC carboxylic acid, NH of this guy, lone pair, lone pair. Now you have to draw the alanine as a V. Therefore, the group, it's simple. If you think about this molecule, if this is how the methyl group is sticking out, right? I don't want to use it as a model. Okay. This is how the alanine is looking like. Let's say the carboxylic acid is here, right? That's the NH2, that's the carboxylic acid. This is the methyl group that's sticking out. There is a hydrogen on the back, right? Looks like you're getting the hang of it. This is sticking out toward you, right? If you draw it, upside down, you realize that the methyl group is now sticking behind. What used to be toward you on your whatever side, left side, now once you turn it upside down, it's on your right side. Make sense? Stereochemistry. Okay. That's why we draw it backwards when we draw the molecule slightly differently. Okay. And COOCH3. This is still protected. That is still protected. Okay. So this is a dipeptide. So this is how it's going to be written. It's going to be written as Bach this is the biologist's N Bach. I may be right or I may be slightly wrong exactly. I'm not sure if the Bach is written first or not. Then N Bach glycine. Then the next molecule is alanine. How do they write? They usually write when it's free OH, they write it as OOH. Then they usually put OH. But in this case, it's not an OH, it's an ester. Maybe it'll be written as ONE. I'm not 100% sure. I'm not going to BS with you. I'm not 100% sure. So usually a peptide chain is written from N on the left to the C on the right. This is the N end, that's the C end. Okay, this is how it's going to be written. You can also write it as N Bach G and then A and then OME, methyl. Okay, that's how you write or type. If you have to draw the molecule this way, this is how you draw it. So this is how a peptide, once you attach two peptides, it's two amino acids, it's a peptide, right? So this is how you draw a peptide. Now I'm going to do something crazy, okay? I'm going to just draw like a long chain amino acid, and just for the sake of practice, I'm going to just stick like different amino acids over there, different natural amino acids. So let's draw an amino acid chain here. I don't know how long we can go, okay? So this is, let's say this is an amino acid chain. It's not very straight. Let's fix it a little bit. Let me try to go a little more straight. Okay. I'm not worrying about protecting groups. Let's say we took care of the protecting groups when we synthesized this long chain peptide. We are just kind of like looking at the molecule and studying it. Okay. So don't worry about the living protecting groups. NH2 is going to be something here, which depending upon whichever amino acid it is, then there is going to be a carbonyl, right? This is going to be an amide bond, NH. This is the second amino acid, whatever the group is here, and then there will be another carbonyl. Then there will be another NH. Then there will be another carbonyl. Then there will be another NH. Then there will be another carbonyl, and then there will be another NH, and let's say there is going to be another COH. Okay, let's send our imaginations beyond our galaxy. Let's say the first, since we do not have much room, let's put something small. Let's say the first guy is, I don't know, alanine. So alanine, first amino acid is alanine. Second amino acid, I don't know. I like lysine. Long dangling tail, bushy tail. How many CH2s? 4. 1, 2, 3, 1, 2, 3, 4, and then an amine. That's a side chain, but that starts with a dashed line. N to C, V, then it's a dashed line. The next guy is going to be up. Let's put something stinky. Cysteine. Next guy. Let's put something greasy again. Valine. Little more grease. 1 methyl group, CH3, 1 carbon, 3 hydrogens, 3 carbons, bunch of hydrogens, 7 hydrogens. That's a valine. And then put something else here. I don't know. Histidine. I like histidine for our chemistry. It's important. That's histidine. Okay. So how many, what kind of peptide is it? How many amino acids? 1, 2, 3, 4, and 5. It's a pentapeptide. It's a pentapeptide. If you have to write them out, what will you write? NH2 alanine, lysine, serine, cysteine, valine, histidine. That's it. 1, 2, 3, 4, 5. And then what biologists do, they don't, I'm not going to say anything bad. They don't change my tone. They don't distinguish between the OH and a carboxylic acid. They think OH means carboxylic acid. We don't think that way, but then we'll take their word or vision. You don't always fight. Pick your battle. So this is your pentapeptide. If you had to write with single letter alanine, lysine is not L, lysine is K, A, cysteine is C. That sounds like a dog breed. Is there like something? Valine, histidine, OH. That's enough. I'm hungry. I deserve lunch. I'm overtiming right now. Okay, so I'm going to take a picture. I'm going to post the pictures. I'm going to process the video, and I will see you guys tomorrow at 5 o'clock. I'm working on a worksheet assignment. We'll see if I can give it to you guys tomorrow, or maybe it'll most likely happen on Thursday.